let's talk about how can we actually deliver this kind of capabilities. And I want to talk a little bit about this somewhat new, it's no longer new, I would say it's trending class of software systems that are called stream processors or in-stream processing. And let me tell you, what it is and how it works and how does one go about building these kinds of systems. And I will start by moving through this stuff quickly because I don't have that much time. But in general, if you look at sort of a landscape of big data systems, it's always more than one system. It's actually quite a complicated workflow. We used to talk about data warehouses a lot, right? Data warehouse is kind of the old world term. The new world term is data lake. It's a modern way to think about it, but basically what we want is we want to collect the data from everywhere. And we want to put it in one place. And then again, modern term for it is data lake. And then we need to define, rivers and streams of how that data actually gets to that lake. Broadly speaking, there is two ways to get there. A lot of times what we want is we want to get data from other systems. And we want to load that to that data lake. And we want to be constantly doing this because the systems keep generating new data. And it's typically done in some kind of a batch processing mode. You write some kind of ATLs, right? There's some people here who make a living by doing this. And you basically write a lot of data transformations that take them from sometimes thousands of different backends and load them up into this new data lake. And you design it right so that you can query them and you can run models, but then you still have to worry about how to get the data. And now there is this second world. And the second world says, well, there's these events that are being generated from source systems all the time. And this is where a lot of Internet of Things stuff come in, right? So why don't we capture these events and right away, the minute the event happened, put them in our lake and apply the models and then do something with it. So this is more of a real-time processing, right? This is batch processing, this is real-time processing. And a lot of times things start as batch processing, and then you can replace a lot of these ETLs essentially with kind of a real-time flows. And once the data is in a data lake, you want to exploit it. You want to identify patterns. You want to take advantage of it. So there's a whole world of kind of a classic BI tools. And then there is this new world that I could call data sciences, right? Things like machine learning, things like deep learning, various machine vision and other ways of exploring the data automatically, not through the work of a business analyst. And once you make sense out of it, you kind of have two ways to get advantage of these patterns. There's these online applications like shopping carts and product recommendations, things like that, where you try to capture more of a customer wallet. There's a lot of technical support, call center and first response and fraud detection, things like that exploit the data as well, right? So this is like a big picture. Then the kinds of things that I'm talking about is really in these parts of the bucket, right? So I'm not going to talk about classic Hadoop infrastructure. I'm not going to talk about classic batch processing. That's kind of, this world. I want to talk to you about the real-time piece. How can you capture an event at the source? How can you analyze that event at the source? And how can you act on that event at the source? What is stream processing sort of ideal for? It's ideal for these kind of four things. Number one, this real-time data ingress, right? If you want the data to end up in a data lake, don't wait a day. Don't wait till next night. Put it there right away. Just as it happens. Kind of basic stuff. Second is this real-time identification of a 1 in a million. It's called actionable insight. Good example is a fraud detection. You have Visa processes. I know because I wrote fraud detection for Visa a couple of times in my career. Processes close to several, 20,000 credit card swipes a second. That's a lot of credit card swipes, right, across the board. But tiny portion of them is fraud. Now, if you know that something is fraud, you actually need to stop the credit card transaction, right? You only have about a second to do that. Because once you swipe, right, you have about a second that authorization takes place. You only have that much to identify if that's a possible fraud or not. Most of the transactions you have to let through, some of them you have to stop. So a transaction that you have to stop, we can call an insight. Insight is identification of one thing that matters. And a lot of the nature of this stream processing is that you've got lots and lots of events. You have to filter out most of them because it's a noise. But then you have to identify just the one that you care about and then respond to them. So identification of these just tiny fraction of things that matter is very effectively done in the stream processing and probably can't really be done effectively in any other way today. And then, of course, once you know that you have a fraud, you want to respond to it right away. So generating that response. And then another increasingly important use case is this real-time learning. As you notice new data patterns, you want to adopt your algorithms. So how does that work? In general, they work. This is how almost any stream processing system will work. You got these events coming up at you, and so you need to have a very scalable and fast message fabrics that can capture these events and cache them and store them and get them ready for processing. Then there is an actual stream processor. And there is a great number of them on the market. Seems to be a renaissance for them. So there is, in the latest Hadoop world, I think 5 new stream processing frameworks were introduced by different companies. Once you're done, you have to create results and deliver them somewhere else. You tend to need a couple of operational stores. Everything here happens in memory. All the processing that happens in memory, it happens in the address space. But sometimes you need to go to the databases. You typically need to do some very quick lookup of things like reference data. So things like Redis or Cast or Ignite are really good data stores for key value type of storage. And then you often need operational store for more complicated, maybe intermediate results or some kind of a larger set. So this is a very typical architecture. And what makes stream processing work is really this. When you have input events and you have results, you have to apply quite complex mathematics to it. And until recently, it required very sophisticated programmers to write this logic. The breakthrough that we've achieved in the last few years and the impact of platforms like Spark streaming that I'll talk about, that creates a very simple programming model that can be used by anybody, that can be used by, I would say, non-specialist programmers. It's something that people can grasp easily. General purpose programming language. You can do it in Python, you can do it in Java, you can do it in Scala. These are convenient mathematical libraries. And the way it works is that you can get very complex behavior, but essentially piping together some very simple operations. You can put a series of filters that are gonna, kill off a bunch of not interesting events. And then events that are interesting, you can put them through sliding window analysis, or you can put it through aggregators, or you can put it through other modules. And essentially every one of them is simple, and this is just a library code. And as a programmer, your job is just to string them together. And it's a lot easier than, you don't have to write complicated data science algorithms, you don't have to write complicated data structures. That work has been done for you by the library.
That's happening in the backend, correct?
Yeah. So, stream processing frameworks essentially dramatically simplified the requirements for the programmer to write these kinds of algorithms. And it opened up the market for a lot more business applications to be written with these technologies. We have used a lot of different technologies, and we sort of came up with some know-how of what works, what doesn't. And then what I do as a CTO of company, I have a program to basically create and publish blueprints. And the blueprint, as I said, is just a reference architecture for classes of business problems. So I wanted to do a reference architecture for in-stream processing system, and this is what you see today. My goal is to create something that will be quite scalable. The system should be able to process literally, hundreds of thousands of events per second effectively. They have to be cloud ready, and what I mean by cloud ready, they are cloud independent. You can run them anywhere. You can run it on Azure, you can run it on Google, you can run it on Amazon, you can run it on internal data center. Infrastructure is your choice. I have a whole portion of the talk that talks about how to achieve it. We probably don't have time or interest to get into it, but that's actually a fascinating topic in its own right. It has to be production ready, right? So we've done it before. We know what works. It has to be done for mission critical use, so no single point of failure, massive scalability, reliability, all these things need to be built in. Because really that's where the challenge is. There's a lot of cool technologies in open source communities. How do you make it work 5.9 on a Black Friday at the Macy's scale with 100% availability? Our choice of technologies. And I have to say that this blueprint, we published it a year ago. We are working on the next generation and we'll make some different choices this time around. But about a year ago, this was our choice. For the message queue, we chose Apache Kafka. It's everything here is best of breed. So these are actually very non-controversial choices. And this is why it's a reference architecture is probably, majority, 90+% of the actual stream processing systems will look very much like that. So Apache Kafka for massively scalable, lightweight, and memory messaging. Apache Spark, streaming, for the streaming processor. We talked about this a little bit in the beginning. I often get questions, Storm versus Spark. We can take another stab at it at any point in time. You could absolutely do it with Storm. As a matter of fact, we did it with Storm some time ago before. But the main reason why Spark is popularity, support for mainstream programming languages, and ecosystem. This is really, the industry went Spark away. And Storm is kind of lost, and that's really the only reason why. Not because Storm is bad, but because this is simply an easier thing to do when you have a wider access to the labor market. We can deliver these insights in a variety of different ways. We can put it in somebody else's message queue. We can dump it in HDFS files so that you integrate with Hadoop. You can put up REST API so anybody who wants to can come and pull it. The key message that I want to deliver here today is to say the real value of the reference architecture are not even these big boxes. Use Kafka here, use Spark here. It's how do you actually integrate and configure all of these clusters together so that you have a single platform that together, end-to-end, has no single point of failures, no bottlenecks, built-in scale, completely lightweight, containerized and Dockerized, deployable on any cloud, right? And how do you, from an operational support perspective, what's the topology that will work? Now, you have to put a lot of technologies together, which clusterize and operational support in completely different ways. If you're using Redis, it's a master-slave. If you use a Cassandra, it's a peer network with at least 3 nodes. If you're looking at Spark streaming cluster, it works its own way. If you look at Apache Kafka cluster, it works its own way with partitioning and other things. So there's a lot of ways to do this wrong. There's few ways to do it right. This is where experience is indispensable. And this is why we are investing the time that we're investing to actually show production-ready configurations.